Hi everyone, I'm Pietro Frigo, and today I and Emanuele are going to present you our talk, A Journey into the Secret Flows of DRAM RowHammer Mitigations. First of all, who are we? Well, we're both PhD students at BUSEC, which is the system security group at the Vrije Universiteit in Amsterdam. And the two of us have been investigating RowHammer for the better part of the past 4 years. Today, we're going to discuss the results of our last 2 years of work on this topic. So what is this talk about? Well, clearly, this talk is about RowHammer, and I guess you could have imagined that. But more precisely, in this talk, we'll focus on what was supposed to be RowHammer-free DDR4 memory. Indeed, memory vendors claim to have solved the RowHammer issue once and for all by introducing DRAM mitigations. So today, we will dive into the details of these solutions that were previously unknown, and we'll tell you how we reverse engineer them. As you can imagine, we wouldn't be here today if we didn't break them as well. So we'll then tell you how we did that, and we'll touch upon their effectiveness. But to discuss their effectiveness, we need to first understand what was available out there as a possible defense. So before doing all this talk about the new DRAM mitigations, we'll discuss about both software and hardware mitigations were being proposed in the past. Now, since in this talk we're going to go into the details of a lot of this DRAM circuitry, we'll now give you some context and some background information about DRAM and RowHammer itself. So let me start with DRAM. When you think about DRAM, you usually think about something like this, which is a DIMM. And you know that somehow the data is being stored in here, right? Well, the data actually is being stored inside these ones, which are the chips. And inside the chips, you have another structure, which is called bank. And every chip contains multiple banks. Now, a bank is simply a bidimensional array of memory cells. And a cell contains a capacitor and a transistor. Now, the capacitor is where your data is being stored, whereas the transistor is the gate to this data. Every cell contains a single bit of information. And when you want to perform memory operation on this data, you need to rely on these other two circuits, which are the row buffer and the row decoder. And now we'll see how these are being used. So let's take one step back and let's consider your normal C program where you say you want to perform the reference of a memory address, right? Now the CPU can handle these addresses, right? But then when you take into account the DRAM subsystem, this address doesn't mean anything for DRAM itself, right? So what you need to have is another component inside the CPU, which is the memory controller, which basically acts as a bridge between the CPU cores and the DRAM subsystem itself. And what it does as a first task is translating these addresses in something more intelligible by the DRAM chips. So, for instance, in this case, the address A1 will translate into bank 0 and row 1. Now, after the memory controller knows that this is the real address you want to access inside memory, it will say, okay, I want to perform a memory read or a memory write at this address. So we'll just communicate over the bus. So now let's go back inside the bank. In the bank, now we're inside bank 0 clearly, and you will get to the row decoder an operation which is called activate to row 1. An activate command is what is needed to perform any operation on the data being stored in memory. And it consists in basically bringing the data down to the row buffer. And this happens by basically toggling the voltage of this line, which opens the transistor that blocks the data. And once the data is there, it will be connected to the bit lines, which is the one connecting it to the row buffer itself. Now, once the data is in the row buffer, you basically discharge the charges of the capacitor inside your own row, which means that the data is not stored in the row anymore. So what you need to do to prevent data loss, clearly, is to restore the data inside the cells themselves. And this is done by another operation, which is known as precharge. And the precharge command is basically the inverse operation of an activator. And what you do basically is, once again, you toggle the word line. And after that, you change the voltage on the bit line so that the data will flow back into the cells themselves. Now, since the data inside memory doesn't last forever because the capacitor leaks charges over time, the memory controller is also in charge of performing another operation, which is the refresh operation. And the refresh operation is basically an activate followed by a precharge. And this basically allows the DRAM subsystem to maintain the data for a longer period. Now, by DRAM standard, it is defined that memory vendors need to provide a retention interval of at least 64 milliseconds. And this means that inside the bank, the memory controller needs to refresh every row every 64 milliseconds. Now, clearly, if we would do that at the end of a 64 milliseconds in retention interval, this would create a denial of service attack on your own DRAM subsystem, because it would mean that at the end of the 64 milliseconds, you wouldn't be able to perform any other operation apart from the refresh. So what the memory controller does is it batches the refreshes in smaller batches, and it refreshes only some rows every 7.8 microseconds. And 7.8 microseconds is known as TREFI, and TREFI is one of the parameters that are defined in the DRAM standard. Now, what about RowHammer though? Well, as we said, DRAM is supposed to retain the data for at least 64 milliseconds, right? Well, what researchers have discovered is that if you perform specific access patterns inside DRAM, you may be able to trigger leakage a bit faster than that. And the most common access pattern, which is known as double-sided, consists in accessing two aggressor rows. And these two aggressor rows wrap in the middle another row, which is the victim row. And if you access them fast enough, you may be able to trigger leakage in the middle row much faster than the 64 milliseconds. Which means that if some cells are mode vulnerable, you may be able to trigger data corruptions in the rows in the middle. Now, why is this important for security though, if they're just spurious errors? Well, it turns out that they're not really an error that happens randomly. But indeed, if you find a cell which is usually prone to fall victim of RowHammer, you can trigger this bit list multiple times, which means that this bit list is actually repeatable. So after its initial disclosure in 2014, the security community picked it up quite fast and understood the potential of this vulnerability. And the first thing they did was trying to figure out what could you do with it. So they tried to figure out if you could bypass the common privilege boundaries, such as a supervisor or a hypervisor. And the first exploit came out just 1 year after its first disclosure by Google Project Zero. And basically was able to gain root privileges by a normal application running on the system. Not so long after that, multiple exploits showed it was possible also to break the separation between kernel and hypervisor. And not only that, but people have shown it was also possible to trigger bit-lists from a sandbox environment. And this brings us to the first axiom of RowHammer, which is privilege boundaries are a social construct. Now, apart from this joke, this is actually quite serious, because as we just saw in this previous slide, what this all translates to is basically the death of memory integrity. So after we state memory integrity is dead, the question then becomes, how can we get it back, right? And this is where we start with looking into defenses. So the first stage of the defenses are clearly software-based defenses, because they're the easiest one to deploy. And the first one that got proposed right after the discovery of RowHammer was disabling flashing instructions. And what do we mean by that? Well, as we said, in the CPU, you have the core that performs memory accesses, and the memory controller takes care of these ones, right? So in your code, you would have simply a tight loop with a reference of two pointers belonging to two different rows, right? Well, it's not so easy, because after you perform the first access to these two rows, data will be stored in the cache. And if the data is in the cache, this means that the channel from the memory controller to DRAM gets disrupted. But luckily, in most modern architecture that are available today, you have explicit flashing instructions to invalidate the data inside the cache, like the CLFlash instruction. So if you use the CLFlash instruction, you basically remove the data from the cache, and this allows you to trigger bit-lists once again, because you go back to memory to fetch the data every time. Now, clearly, the first defense that was proposed was, well, what if we disable this flash instruction? You disable the flash instruction, you break once again the channel between the memory controller and DRAM, right? Well, not really, and we already saw it implicitly when talking about all the different exploits. And this is, for instance, when you perform an exploit from a sandbox environment. From the browser, clearly you don't have access to this CLFlash instruction. And how you do this is by performing, for instance, cache eviction. And this consists in basically trying to push out the data from the cache, so the cache lines that contain row 1 and row 3 will be pushed out of the cache so that you can access it once again from memory. And apparently this is already fast enough to trigger bit-flips. So this mitigation doesn't really work. Now, another option that was proposed was to perform tracing via the PMU. And the PMU is the performance monitoring unit. Now, the idea is that the CPU contains a whole bunch of counters that allows you to observe events on the CPU. And the idea you would have in mind is you want to observe accesses to memory and try to detect anomalies in these accesses. Luckily, most of the CPUs nowadays provide a whole bunch of different counters that counts misses in the last level cache or memory requests. And by just observing these counters, you can see if you have an abnormal number of requests to memory. And the idea is after you observe this thing, what you will do is try to refresh the rows that are being targeted, right? Now, the problem with this idea is that doing tracing from software is actually quite expensive. And for these reasons, you clearly need to trade performance for security. How would you do that? Well, the easiest way to do that is to tailor to specific patterns. So for instance, what you could do is trying to detect when someone is doing double-sided or something else. And this clearly, and it has been proven in the past, it's very easy to fool. Because if you tailor your tracing mechanism to specific patterns, then everything that deviates a bit from the standard pattern, it will not be detected. So also this one was not really an ideal situation. So then we just saw that basically it's very hard from software to prevent bit flips from happening. So the next stage that came out in this history of software defenses against RowHammer was, well, if you cannot prevent these bit flips, can you at least stop the exploitation of these bit flips, right? And it sounds kind of reasonable. And the way this was proposed was by trying to propose physical memory separation. So what do they want to do was basically trying to enforce the same separation level that if, for instance, you have in the CPU between different user space or supervisor levels, and basically enforce the separation also inside DRAM. How would you do that? Well, the way you can do this is by placing some guard rows in between the different privilege levels. So what you will do is you will store all the application data above the guard row, for instance, and your Linux kernel data below the guard row. Now, this theoretically should prevent attacks from EL0 to EL1. However, this doesn't prevent attacks between different applications in the same context level. So for instance, multiple applications could attack themselves. So you could trigger a bit flips from your browser and attack, I don't know, your Word application or whatever. And so this is already theoretically should be better than nothing, but still you allow a whole different bunch of attacks. Another solution, which was a bit more fine-grained, was to try to basically get this idea and make it a bit more precise. So the idea was to have a guard row in between every other safe row. Then in your physical address space, what you would do is remap this memory into two regions, which are a safe region and an unsafe region. And the kind of neat idea behind this proposal is that you don't need to throw away the data in the unsafe region, but you just need to check for its correctness, right? So you would consider the safe region as your main form of memory, where you store most of your data. And on the unsafe region, you would store data that either you care less or you use less often. And then before accessing this data, you would rely on error correction or just some error detection mechanism to figure out if the data was corrupted. Now, what are the limitations behind these solutions? Well, first of all, the first limitation is that bit flips can occur on rows farther away as well. And because of this, it means that basically you might need to have way more guard rows than what you would expect, which means that the performance impact are quite high. If, for instance, if you want to use the approach of doing the safe and unsafe region. And the second limitation, which is probably the most problematic for most of the software solutions that we discussed here, is that the fact that inside the memory you might have some unknown geometry of the location of the DRAM rows. So what is the problem here? Well, earlier we were talking about DRAM rows, and we were saying that basically when you perform an activate command, you will open a single row. Well, actually, that's not exactly what happens inside DRAM. But indeed, inside DRAM, what you have, you might have the same row wrapping around into different rows. Now, this is completely oblivious to the CPU and the memory controller itself. So the memory controller will still send an activate command to a specific row. However, inside DRAM, the circuit might be designed differently, and the data you will get is the correct one, clearly, but you just don't know where the data is coming from. And for these reasons, though, since you want to implement the defense from a higher level, so from the software, you should be aware of these different designs. And this becomes kind of unscalable because if different vendors implement different remapping strategies inside DRAM, it's impossible to keep track of all of them and figure out how to do this. So also this solution is not really ideal. So this is all for the software defense side, and we saw that none of them is actually as effective as they were meant to be. Now I will leave the floor to Emanuele, who will discuss with you most of the hardware defense that have been proposed in the past, and then we'll take it over and dive into the details of the new DRAM mitigations. Emanuele, take it away.
Hi everyone, I am Emanuele Vannacci, and during this second half of the talk we are going to discuss and explore a different class of defenses, or rather we are going to talk about hardware mitigations. So the first mitigation we are going to talk about is ECC. ECC memories are kind of memories that are mainly deployed in server environments. How can we find if a memory module supports ECC without looking at the specifications? Well, it's pretty easy to recognize ECC memories because if you look at the physical module, you can find an extra chip compared to non-ECC memory modules. And on this ECC chip, the memory controller, the system stores extra information, allowing the system to correct and detect errors. In current designs, the only ECC-aware unit on the system is the memory controller. And when the CPU wants to write some data in memory, the memory controller itself appends a certain amount of extra bits of redundant information for error correction and detection. So server memory comes with this capability. If an error is detected, for example caused by a RowHammer attack, the error can be corrected. ECC systems can correct one error, while for example a 2-bit error causes a denial of service. However, recent work shows that it's possible to trigger bit flips in such a way the errors are undetectable and uncorrectable, making the attack even more dangerous than a denial of service attack. However, ECC is not spread in desktop environment, where it's easier to find another class of mitigations, and I'm talking about refresh-based mitigations. One original RowHammer countermeasure proposed is the adoption of a double refresh rate. That means refreshing all the rows in the DRAM every 32 milliseconds. So basically, the memory controller issues a refresh command every 3.9 nanoseconds instead of every 7.8 nanoseconds. While in practice only a small percentage of systems adopt a double refresh rate by default, modern systems allow, for example, to set up the refresh rate by the BIOS, or even in the JTAG standard, it's specified that when the DRAM temperature exceeds 85 degrees, the system automatically turns into a double refresh rate. During our research, we often had to check the actual refresh rate, and a way to do it is by timing analysis. Indeed, timing a long sequence of accesses in DRAM and looking at the latency peaks caused by refresh operations reveal the refresh rate. And for example, in the plot, in the current slide, you can see that a double refresh rate results in some latency peaks. So looking at the blue plot, that is a standard refresh rate, it's clear the difference with a double refresh rate resulting in twice the amount of peaks. Likely has been shown that doubling the refresh rate could not completely mitigate RowHammer effects, and we confirmed these results. Indeed, even shorter refresh interval, a longer refresh interval, could be necessary. And increasing the refresh rate does not come for free. Indeed, frequent refreshes cause performance degradation, mostly in terms of energy efficiency. So nowadays modules spend 2 to 5% of the time just performing refreshes, and increasing these numbers to 10 till 35% will not be feasible, not for laptops, not for smartphones where you would see your battery life dropping faster, not for data centers when energy consumptions are important and must be taken into account. These are the main reasons why doubling the refresh rate is not an optimal solution, and it's rarely considered. So another solution is called para, aka probabilistic adjacent row activation. So para tries to reduce the number of refreshes required to mitigate the RowHammer, and to do it, it defines a parameter P. So P, it's a probability, and every time a row is activated and then closed with a certain probability P, the adjacent rows are activated. The main advantages of para is that it is stateless, meaning that it doesn't keep any counters or data structure, and so also the overhead is very low. However, the main disadvantage is that the memory controller has no knowledge of the memory geometry that is required to refresh and to activate the adjacent row. But we have also other kind of mitigations, and can be noticed how the trend through the mitigation design is to reduce the number of refresh operations more and more. So we started with a double refresh frequency when the memory controller issues refresh operation to refresh all the rows in the DRAM array twice compared to a standard refresh rate. Going through para, where you define a parameter P trying to limit the number of refreshes. And then the natural step forward is to try to refresh only the victim rows. So try to identify a RowHammer attempts, identifying which are the aggressors, and then refresh only rows that are likely victims. So let's talk about PTRR, or pseudo-target refresh. That is a mitigation introduced by Intel to protect DDR3 systems. And the key idea is that the memory controller must monitor row activation and then performs a targeted refresh on the victim rows. The disadvantage here is that no details are available. The only source of information is an Intel presentation that you can find online. And here I reported a snapshot of this presentation where it's defined also the concept of compliant DDR3 DIMMs that is unknown what it means. What compliant DIMMs means? The answer can be found in the serial presence detect. So the serial presence detect is a read-only memory chip on the DIMM itself, and it contains some information, like for example information about the manufacturing date, about the manufacturer, about the timing constraints of the DIMM, of the DRAM. And also it includes this field called MAC, maximum activation count, that specifies how many activation a row can afford before the adjacent rows start experimenting bit flips. And this maximum activation count can take three different kind of values. The first is untested, meaning that the MAC is not available. Unlimited, meaning that the DIMM itself is RowHammer free. And this is interesting because it could mean that the DRAM substrate is not vulnerable to RowHammer, but it could also mean that there are other mitigations in place. They're directly implemented in DRAM, and we will investigate this option later. Or a discrete value, for example 300K. So we carried out an experiment to see if the pseudo-target refresh is really implemented. So we picked up two machines. The first one is the one reported in the Intel presentation, and the second one is a desktop machine. So with a Mac value set on unlimited, the amount of flips that we could observe is pretty the same, but setting the Mac value to 400k, we could see a dropping in the amount of flips on the Xeon machine. And this leads us to conclude that pseudo-target refresh were actually working on the Xeon machine but not on the desktop machine, and that the DIMM itself has a capability to support pseudo-target refresh. But we tested also other machines, and we could conclude that pseudo-target refresh is a mitigation that is supported but is mainly dormant and disabled in most of the systems. But why? The answer is that probably there are other mitigations like target refresh. Now we are going to investigate another class of mitigations. So far we have seen software mitigations and mitigation that work with memory controller support, but here we are going to investigate the DDR4 landscape and the in-DRAM mitigations, so mitigations that are directly, completely deployed and implemented in the DRAM circuitry without any support from external components like the memory controller, for example. And here you can see in this slide a timeline describe the introduction of target refresh-like mitigations. So pseudo-target refresh has been introduced in 2013 to protect DDR3 systems, but it's possible to find it also on the first generation of DDR4 devices. While we analyzed a batch of 42 devices, we could speculate that in DRAM target refresh has been deployed only starting from 2016. And for two reasons, our batch, we decided to analyze memory built mainly after 2016 and one DIMM after 2015. So previous reports of bit flips on DDR4 devices questioned the effectiveness of target refresh, and this is the reason why we wanted to investigate more target refresh design. But what is target refresh? So target refresh is not a single mitigation, it's more like an umbrella term. Umbrella term is like a concept, and it defines an umbrella of mitigation that try to track row activations and prevent errors. How? Targeting refreshing victim rows. So there is no support from the memory controller because also the memory controller has no knowledge of the memory geometry, and the solutions are completely embedded in the DRAM circuitry. Target refresh was originally introduced with the JDEC DDR4 standard, but then it was removed in the revision B. However, memory vendors are still advertising RowHammer free memory modules. And this because they are likely implementing and deploying their own solutions. And so the landscape is so fragmented and there are no details because vendors are enforcing the security by obscurity principle. And this leads to difficult to evaluate the effectiveness of target refresh since no real evaluation and assessment is possible. So to study target refresh design, we decided to abstract from the single implementation, and we identified two components that target refresh design should include to work properly. And the first one is the sampler, that is the component that monitors row activations and inform other components about which rows must be refreshed. So for example, the inhibitor get this information, and it can decide to refresh victims, or it can perform other kind of action, like for example remapping. And in this example, we can see a target to refresh controller with a sampler and an inhibitor that they communicate. And the sampler, you can imagine the sampler as a cache, and when a row address is specified, the row address fill one empty slot on the sampler, and then when we can go on, for example, specifying row 7, then row 0, and then row 1. And at this point, when we specify another address, one slot must be evicted from the sampler. And so we can evict also row 7. And if we repeat this sequence of access, we can, for example, hammer row 5 and row 7. So we can evict them from the sampler, and when the inhibitor will ask for our row address to refresh, it will get, for example, R1, but we want to hammer, for example, row 5 and row 7. So this is just an example. To better understand how target to refresh works, we needed to reverse engineer our DIM implementations, but reverse engineering poses some challenges. First of all, analysis from the CPU side is not feasible anymore, because the memory controller provides a very high interface. We cannot specify sequence of commands, we don't have control over optimizations, and we don't have side channels. Because the DRAM is a synchronous device, operation must rely on specific timing constraints, and so we don't have any timing signal. We will need an FPGA-based memory controller, and we found it in SoftMC, an FPGA-based memory controller infrastructure, allowing us to issue specific sequence of commands like row activations and refresh command. So we want to reverse engineering the sampler size. How? Issuing specific commands by SoftMC, and of course targeting more than 2 aggressor rows, because we want to fill the sampler and see what happens. We discovered a new hammering pattern that we dubbed the many-sided RowHammer, in which we basically pick n aggressor rows with n greater than 2, and these are our aggressor rows. So we hammer from 2 to 20 aggressor rows, in contrast to the state-of-the-art hammering pattern. Why? Why it should be clear? To lead the sampler to discard a few rows and then to get flips. So our methodology, we designed an experiment. We picked n aggressor rows, we perform a series of hammers, let's say 8k activations, and after each series of hammers we issue R refreshes. This for 10 rounds, and then we looked for RowHammer bit flips. So after our case studies, we could conclude that target to refresh is enabled, and it's mitigating RowHammer on every refresh command. So it's acting on refresh command. On every refresh command, the sampler picks some row, and or the inhibitor refresh some other row. And the mitigation can sample more than one aggressor per refresh interval. So on every refresh, the sample can pick more than one refresh. And the mitigation can refresh only a single victim within a refresh operation. This is probably because of timing constraints. The more important is that sweeping the number of refresh operations and aggressor rows reveal the sampler size, so we could reverse engineer the sampler size. And then we saw that the sampling mechanism is affected by the addresses of aggressor rows. we found that DDR4 substrate is much more vulnerable than the old DDR3 because we could get bit flips with less than 50k activation per aggressor. So it's possible to overfill the sampler, getting flips, and victim rows may not be properly refreshed by the inhibitor, and this is because we are getting flips. So there are some inhibitor properties, like the inhibitor could be timing based, meaning that it acts on every second, on third or fourth activation on the after the start of the refresh interval, or it could be frequency based, meaning that it acts with a fixed frequency, and the inhibitor could still refresh operation to refresh victim rows. So yeah, we could reverse some DIMMs. We solved the one problem, but yeah, how many DIMMs we could reverse engineer to close the case? So reverse engineering is not scalable. It does not scale. So we decided to go for another approach, and we designed Trespass, and we wrote our paper Trespass in collaboration with the Safari group at ETH of Zurich and Qualcomm. And Trespass is a raw fuzzer, meaning that it's a black box fuzzer, and to scale this approach on many DIMMs and automatically find hammering patterns. So in our hammering pattern, we randomize the number of aggressor rows, meaning that we could hammer 5, 7, 10, 20 aggressor rows, and we could also randomize the location, because we have found that the addresses of the row affect the sampler, meaning that the sampler could it may sample some rows more likely than others based on their address. And we could trigger bit flips or even with Trespass. So we found that target refresh is not secure at 100%. It is discretely effective against state-of-the-art hammering patterns, because we could not find any bit flips with state-of-the-art hammering patterns on our batch of DIMMs. But we found DIMMs that are vulnerable to novel patterns, like the many-sided hammering patterns. The natural question that arises is, what if we combine target refresh with other kind of defenses? So, for example, a double refresh rate. Well, we did it. We still got flips. So doubling the refresh rate is not a solution. What about ECC? We didn't test ECC combined with target refresh, mainly because we were working on desktop environment, but I believe that combining the many-sided RowHammer with techniques described in the ECC ploit paper, where you can reverse engineering the ECC functions and find bit flips that are not detectable or correctable, then combining these two techniques, you can still get flips, probably. To summarize, software mitigations have high overhead most of the case. They lack of memory geometry information, while hardware mitigations are they usually have a lower overhead, but they are hardly deployable. We have fragmented solution. Think about target row refresh, for example, where each vendor implement its own version, and there is missing of a standard. So in conclusion, DDR4 devices are even more vulnerable than previous versions, like DDR3 devices. All major vendors are affected by RowHammer. We found that 90% of the market is affected. And fuzzing can help evaluating the effectiveness of mitigation like target refresh. However, RowHammer is still a problem after almost 10 years, and we don't have a prompt mitigation available for deployment. So this means that an effort from the security community and the industry is still required. Thank you for the attention.
How much hardware engineering knowledge is required to research about RowHammer attack?
Do you want to take it, Emanuele?
Of course. Before this question, I have a quick note. So we noticed a mistake on the slides. When I was talking about the inhibitor that could be time-based or frequency-based, I actually means the sampler. So it's the sampler that could be time-based or frequency-based. Apart from that, about the questions, so of course you need some knowledge about the DRAM technology, so about the DRAM architectures, and yeah, it's really hard to define the actual knowledge you need in this field because you are doing research. So it's always good to have general knowledge about programming, but about also DRAM architecture and engineers in general. So. Yeah, do you want to add something, Pietro?
Is there a certain programming language that is more distinct to hardware engineering?
We coded the trespass in C, but you may do it also in C++ or other language. So a language that allows you to have enough control over the addresses you are targeting. It's enough, I guess.
Yeah, so I think, well, the hardware part, like having hardware knowledge, I think it's useful. For instance, it was useful for us to build a trespass and to do the reverse engineering, but also none of us has actually a hardware background. So we're both coming from a computer science background. And I think it's like it helps, but it's not mandatory. For the exploitation side, not useful at all. I mean, you don't really need to know how you trigger the bit flips. It's mostly to understand, like, for instance, in this case with DDR4 we needed to understand how to get there. Once you know how to get there, you just use any pattern. You can just trigger a bit flips, and that's fine for exploitation. From the programming language, I think it's, yeah, it doesn't really matter. I mean, like, there were exploits even in JavaScript, so, like, I don't think there is anything higher level than that. So, I mean, once you know how these attacks that you build translate to memory accesses, you can do it basically with every language. Clearly, for a starting point, probably it's better to use something like C or any programming language where you can build, like, when you have more control over the memory, as Emanuele said.
All right, wonderful. We've got another question. In your opinion, what sort of software mitigation is most relevant when hardware mitigation is not available?
Well, my idea is that targeted refresh is not so bad in the end because it can really mitigate the state-of-the-art RowHammer attacks. I mean, it is not secure at 100%, but it's an improvement, and I think in the future we will see more and more mitigations implemented directly in DRAM without any support of the system, for example, by the memory controller side. So yeah, maybe targeted refresh in combination with ECC is the best solution for now. What do you think, Pietro?
I think, yeah, it really depends on the support that the machine has. So, as Emanuele was saying, like, targeted refresh, it's quite decent considering like the amount of effort you need to trigger bit flips. I think, like, a possible, like, an interesting solution, which is a bit less demanding in the sense of requirements of the systems, is Para, which is still, I mean, these are they're like in between hardware and software because they're still implemented like at the CPU side. But for instance, like, Para was introduced in some laptops via BIOS updates, and you just basically introduce some extra refreshes. And I think that's pretty good because it doesn't require any any support basically from the DRAM device is just the CPU side, and it just does extra activations, and depending on probability you set, you get more and or less security. On software side, I don't really think there is much you can do. I mean, like, you could design some I don't know, like a specific mitigation for specific use cases. So you want to prevent the exploitability of specific bit flips in the browser, then you can target it directly on the browser itself by doing something with pointers, like trying to avoid the possibility to corrupt pointers or something like that, which is something like what they did for Spectrum Meltdown now. But I don't see it like in software itself to be a possible solution for RowHammer. So yeah, I think it's like probably Para. It would be my best bet for something that doesn't require support.
Yeah, in terms of security, I think I agree. I was more thinking about DRAM mitigations, but if you think at mitigation that you can use with the memory controller support, Para, it's the best solution also for me.
Okay, thank you. And we have one final question for your talk. From an offensive security perspective, what upcoming DRAM technology are you most excited with, and why?
Well, of course, we would like to experiment more with the DDR5 DRAMs coming soon, I hope, because we actually don't know if they will be deployed with some RowHammer mitigations or the same situation that we have seen with DDR4 will be repeated. So yeah, I think that the DDR5 devices are the most
I agree.
waiting for them.
I agree. DDR5 is probably the most interesting bit now because of the trend that Emanuele was talking about also during the talk, that DDR3 was in its own like less vulnerable than DDR4 because it had like less cells inside the memory. DDR5 is going to be even more packed, so most likely the substrate is going to be more vulnerable. So yeah, that's quite interesting. Another technology I think it could be interesting to look at is I think it's called the PIM, which is like a memory with also like in-memory computation capabilities. So it has some microcontroller on the DRAM itself to perform computations, and I think also that one could be an interesting target to look at also for defensive side maybe. Yeah, that I really didn't think about. Like, I think DDR5 at the moment is the most logical step to look into just DDR3, DDR4, DDR5 is complete. LPDDR5 is already out. I discovered last week, so it's something that is worth looking into, I think.
All right, wonderful. And with that, I think that comes to the end of this talk. Thank you so much, Manuel, Pietro, for your talk. I hope everyone had fun. I hope you had fun.